When we talk about beauty, we talk about waves. Today, I'm going to teach you these beautiful things we call waves. So, what is a wave? Wave is a disturbance. Wave is a disturbance that carries energy. The difference between waves and pulse. So, this is, you take a rope and you move it up and down once, you create a pulse. So this is just one pulse on a rope. This is just one pulse on a rope. This is T1, T2, T3. What does that mean? This is one pulse on a rope at different time. So this is pulse. Now how can you create wave? So you create wave by continuously creating pulse by using a rope. For example, you hold a rope and move up and down forever. That means you're creating continuous pulse, and there is another name for it, and we call it waves. We're going to talk about three types of wave right now. Standing wave. All right, so what is a mechanical wave? Mechanical waves needs a medium. You need a medium to move the information or energy from one location to the another location. So yes, you need medium. The EM waves, you don't need medium. So, but it also works in a vacuum. What is EM waves? EM waves is the light. It can carry information in the vacuum, or it can carry the energy in the vacuum. Standing waves needs medium. All right. So now we're going to talk about two types of mechanical waves. One is we call transversal, and one is longitudinal. All right. So transversal, the particles oscillate perpendicular with respect to the direction of the waves. How can I create this disturbance? I can create this disturbance by this slinking. This is transversal wave. The example is water wave. All right, let's start something easy. I have a dot, and if I come back to this dot, how many cycles? 1. What is the wavelength? 1. So then I can do the same thing. I can cut it by scissor, I can make it a straight line, I can move it up and down once, I can create a transversal wave. That means how many cycles over here? Still 1. What is the wavelength? 1. All right, so with this understanding, you're going to now tell me how many cycles over here. 1, 2, 2.5. So 2.5. This is how many cycles over here. All right, this is how many cycles? 2.5 cycles. Now, what is the wavelength? Wavelength is also 2.5. Now, if I do remove this one, now how many cycles? How many cycles now? Of course 2. And what is the wavelength? Of course 2. Now a few things I'm going to help you understand on transversal wave, and that is this one, for example, we call crest, and this one we call trough. All right, so now let's understand the wavelength. How can we calculate the wavelength? All right, let's see. 1 cycle, 2 cycle, 3 cycle, 3.5. And how many wavelength? Of course 3.5. So let's find that out. How many way you can get 3.5? 1 to 5 is a wavelength. Okay, let's see. 2 to 6 is a wavelength, and 3 to 7 is a wavelength, and 4 to 8 is a wavelength, and 5 to 9 is a wavelength, and 6 to 10 is a wavelength. You get the idea. So these are the wavelength. This is the wavelength. So this is the wavelength. So crest to crest is a wavelength. Trough to trough is a wavelength. All right, or successive point to successive point is a wavelength. Water waves. Waves is an example of transversal wave. Okay, now let's see. This is how the water wave look like. All right, so what are the things we have? We have, of course, we talk about the wavelength. So this is the wavelength. So this is the depth of the water. So water waves is actually two types. One is shallow and one is a deep water. Shallow water and deep water. Now let's do the shallow water first. Shallow water, when d over lambda, so we put the d over lambda. So when the d over lambda is less than 0.05, then we consider that a shallow. And when d over lambda is more than 0.5, then we call it the deep water. Now let's first write down the formula. So this is shallow and this is deep. Now first find the lambda. So lambda for the shallow water would be, this is, let's say, G, and this is, let's say, D, and this is T. And this one would be G T square over 2 pi. Now from here we're going to find the velocity as well. So the velocity, we know lambda frequency. Now so velocity is, lambda is what? GD, and frequency is 1 over t. So tt cancels, so velocity is gd. This is the velocity. Now let's find the velocity over here. So velocity is lambda f. So velocity is lambda is gt square over 2 pi, and then f is 1 over t. T cancels, so it's gt over 2 pi. So this is the velocity for the deep water. Now say this is the water, and the period is 8 seconds. Okay, period is 8 seconds. We are doing a case study. Period is 8 seconds. There are two types of water, and both of them period is 8 seconds. This one depth is smaller. Depth is 0.9 meter, and this one, let's say depth is 60 meter. All right. So let's see, we're going to solve these two problems. One is 60 meter, one is 0.9 meter. So we think that 0.9 meter would be shallow, but we have to check that. And how can we check that? It's very simple. We're going to use the lambda is equal to G D T. So lambda is G is 9.8, D is of course 0.9, and T is 24 meter. Okay, now we're going to use the other formula, which is d over lambda. So d is 0.9 divided by 24, which is 0.04, which is less than 0.05. So this is an example of shallow water. So we're going to have to use this formula to find the velocity. So velocity is g and gd. So g is 9.8. and d is of course 0.9, 2.9 meter per second. Okay, so this water velocity is 2.9 meter per second. Now we're going to do the other one. Let's do the other one, and right here. So this one is right here. So how can we do that? So we have the depth is 60 meters. So we think this is an example of the deep water. Is G, the period is square over 2 pi, so 9.8 times 80 square over 2 times 3.14, and this is 100 meter. So we're gonna say d over lambda. D is of course 60, 100, which is 0.6, which is greater than 0.5. So this is an example of deep. So then we have to use the velocity we did earlier. Gt over 2 pi, 9.8 over 2, 3.14. That is 12.5 meter per second, and that is the velocity here, 12.5 meter per second. So you saw two examples we did. Now hopefully you understood transversal wave really well. On longitudinal, the particle when you, for example, when you move a slinky back and forth, the particles in the slinky oscillate parallel with respect to the direction of the waves. I'm going to make it longitudinal wave, and what is the example of longitudinal wave? Is the sound wave. When I talk, you hear is because the sound coming out from my mouth vibrates the air molecule, and that one vibrates the other air molecule, and that one vibrates the other molecule, and that one vibrates the other molecule until it gets to your ear. So what happens if you remove the ear? Then, well, the sound wave cannot move then. What does that mean? Sound wave needs a medium. Sound wave needs a medium to transfer energy from my mouth to your ear. If you remove the ear, the sound wave won't be able to transfer anything and you won't be able to hear anything. This is longitudinal wave. The example of this wave is the sound wave. Our case study would be sound wave. So let's understand the longitudinal wave. So let's copy and paste this a few times. If I do copy and paste one more time, what do I get? I get, let's put some point using different color. So put A over here, put B over here, put C over here, put D over here, put E over here, put F over here. Call this one compression. Later on, when I drop slinky from my hand, you're gonna see compression is really very interesting topics. So slinky will have the top and bottom, and then when I drop it, which part will touch the ground, top, bottom, or both, top and bottom at the same time. Very interesting case study and experiment we're gonna do. So I'm gonna be very excited to sharing this with you. That is coming up. Now, what do we call it? We call it compression. Compression. There is other word, condensation. You can call it condensation. So this is rarefaction. Now, how many wavelength over here? Let's see how many wavelength. So from compression to compression, one wavelength, two wavelength, and 2.5. So 2.5 wavelength. How many way you can get 2.5 wavelength? So let's say A to C is equal to, of course, B to D is equal to C to E, all right, is equal to D to F. So 1, 2, 3, 4 way you can get 2.5 wavelength. Now we're going to do case study, and that is sound wave things. What are the two things? Then one is bulk module, and of course the other one is called density. The bulk module sometimes called pressure, and sometimes it also called compression. All right, and there is a notation for bulk module, and density also have a notation rho. The bulk module has an equation, because what is the pressure? When we talk about pressure, we talk about force over area, and when we talk about density, we talk about, of course, the mass over volume. All right, so let's see what contributes what when we talk about sound wave. Before that, I'm going to give you some understanding of sound wave. Sound wave, when we change the medium, for example, sound wave needs medium because sound wave is a mechanical wave. It needs medium, and it moves faster in different mediums. So let's check 3 medium. What can be example of gas? I think air. What could be example of liquid? Water. What can be an example of solid? I don't know. Iron. Okay, now gas, of course, gas is like the particles, they spread around mile away from each other. Liquid is, they are not that tightly bound, but the solid, they are very close to each other. They are very close to each other. All right, this one is stiffer, and this one is the steepest. All right, what is steepest to do with this? Well, the more steep it is, then the velocity would be greater. For example, velocity in the gas is smaller than velocity in the liquid, which is smaller than velocity in the solid, which is iron. What does that mean? If I take you to the railway station, and if I stand over here and 20 meters away, my sibling stand up and I say something with 20 hertz, my sibling ain't gonna hear me. However, if I knock the railroad, the iron, with a hammer with 500 hertz, then if my sibling put a ear on the red line, my sibling will be able to hear it, because the sound wave, the velocity of sound wave moves faster in the solid than, of course, in the air. But anyway, we have to prove that. So let me give you the formula. If I don't give you formula, how can you find out? So let me give you the formula. So let's find the relationship. So B is, of course, the bulk modules, and P is density. So P is M over V, and then B is F over A. Now, if the mass go up, then of course, if the P go up, what does that P means? Density go up, mass go up, then inertia go up. What does that mean? If mass go up, then velocity go down. What does that mean? And velocity is equal to 1 over what? 1 over P, 1 over density. All right. What about here? If the force go up, then bulk module go up. If bulk module go up, force also go up. So they are proportional to each other. So we can put together a formula for the velocity. Okay. So the velocity is then this is B and this is velocity. So velocity is then B over P. So now we don't know whether we need to modify this formula. So let's see whether we need to modify this formula. We're doing very simple dimensional analysis. You know Einstein, right? Einstein had hypothesis E equal to mc squared, E equal to mc cubed, E equal to mc4, and dimensional analysis he used, and he used dimensional analysis to find that E equal to indeed mc squared. Now what is M over here? Kilogram. What is B over here? Cubic meter, right? Let's see over here. What is F over here? Newton. A over here is square meter. N is kilogram meter per second square, and this is meter square. Now we're gonna put on top of each other. So the velocity is B. What is B? B is kilogram meter second square, meter square, and of course, the P is kilogram over kilogram over cubic meter. So now if we do math, what do we get? Kilogram meter second square, meter square times cubic meter over kilogram cancel. So we have meter times meter square over second square. Now if we take the square root, we get meter over second, and that's the velocity. So it seems like we have to modify this formula. What does that mean? We have to write V is equal to bulk modules over P. Of course, this is the velocity of the sound. That means, of course, as we see, the sound is small over here, big over here, very big over here. Hopefully, this will allow you to solve and prove that this is in fact true. As you see, we have fast antinode. That means we have 2 nodes and 1 antinode. The antinode has a maximum displacement. We created the second harmonic with 2 antinode. So the wavelength for second harmonic would be 2L over N. In this case, N is 2 because 2 is the antinode. When we talk about standing waves, we usually start our conversation with the wave we know and we love. So this is a wave. What type of wave is this? This is just a transversal wave. It has a beginning? No. Does it have ending? No, of course not. However, to make it a standing wave, you have to have a beginning and you have to have ending. So how can we do that? Well, that's very easy. You can have a beginning, and if you can have ending very easily. All you need to do, put a barrier. If you put a barrier, all right, then you have a beginning and you have an ending. So you have a barrier. So what the barrier does to the wave? Now this is an incident ray. When it hit the barrier, it bounce back with the same magnitude but opposite direction. We human perceive that when you look at that, it look like a standing wave, and we call it a standing wave. Of course, these two end does not move, so we don't call does not move, we call them node. So we have two node, and of course this point has maximum displacement, they move too much, so we call them anti-node. In fact, anti-node has something to do with the harmonic series, and that's what I'm going to explain next. So we're going to talk about harmonic series. So when we talk about harmonic series, we talk about two things, lambda and the frequency. So this is the nth wavelength for harmonic series. This is the nth frequency for harmonic series. What we talk about, let's consider a guitar. This is the same guitar. I'm going to put it 3 times because I'm lazy. All right, 3 guitar, I'm going to put it 3 times just because I'm lazy. All right, so come on. So 3 guitar. Now third harmonic, 1 2 3 3. All right, so now what is the wavelength over here? Wavelength over here is half lambda. What is the wavelength over here? Wavelength over here is just the wavelength, right? So it's just one wavelength, it's just one. And what is the wave? 1.5, so 3/2 lambda. So now we're gonna try to find this equation, this beautiful equation. How? We're gonna write this one in terms of lambda. If we do that, we see 2L. We're gonna write this one in terms of lambda, so we see of course L. We're gonna write this one in terms of lambda, we see 2L over of course 3. Now we see the pattern. If you don't see the pattern, then well, you should. This is 2/1, 2L over 1. We can put this so multiply this one by 1 and then multiply this one by nothing. Nth wavelength for harmonic series is 2L, 2L, 2L of course, and then this is the node, 1 2 3. So 1 2 3, so we can call n is anti-node. So this is the nth, this is the 2L over n. So this is the nth wavelength for harmonic series. Now we're gonna find the frequency. All right, so this is the equation, 2L over n. So now what is the lambda velocity? Velocity is lambda f, is of course velocity over frequency. Okay, so we're gonna replace this one by velocity over frequency. So velocity over frequency is 2L over n. So we're gonna cross multiply 2L, f is nv. So f is nv over 2L. Now if we come over here, what do we see? We see that velocity is lambda times frequency, of course. Now lambda is 2L. We already have that, so we can replace that. Velocity is 2L because lambda is of course 2L, so 2L f. So what is f? F is velocity over 2L. Okay, so this is f of what? F of fast harmonic. So fast, what is the frequency of fast harmonic? V over 2L. So V over 2L is what? The frequency for fast harmonic. So what is the frequency for nth harmonic? Is NF1. So this is the two equation that I promised to give you. This one is 2L over n, and is the anti-node, and this is the frequency of the harmonic series, and F1 is the frequency for fast harmonic. All right. When we talk about EM waves, we talk about electromagnetic waves, and electromagnetic waves need no medium. All right. Let's consider a negative charge and let's consider a positive charge. So field line goes from positive to negative, of course. Now let's say these two charges, they move, they oscillate each other. So if they do oscillate, so this is negative, this is positive, they change the location. When they change the location, at some point they are together. So at some point the negative one is negative 1 and positive 1 are the same. So then the field is 0. And then the positive 1 back to be over here and negative 1 back to be over here, then fields of course like that. So this is E field, this is electric field, and how that helps us to draw the electric field with respect to the time. So electric field with respect to the time would be this, and this would be the electric field. All right, so electric field at location A, location A would be to the north, and electric field location B to be to the south. And for simplicity, we don't have to show that because it propagates to the right, electric field. All right, so now we're going to talk about the magnetic field. So in the wire carry current, all right, and the direction is to the north, then you can use a right hand rule to find the direction of the magnetic field. So if you use the right hand rule, use the thumb up, and you curl your finger around the wire, you see that this magnetic field is going into the page, and this magnetic field is coming outside the page. So this is the magnetic field for this wire which carries the current from south to the north. Here electric field is 0, so magnetic field has to be 0. If there is no current, there is no magnetic field. Here is opposite, okay, by right hand rule. You curl your finger, so this one goes inside the board and this one coming outside the board. So this is the magnetic field. Now I'm going to draw the magnetic field over here. It's going to be a little hard to draw, but I'm going to try. All right, so the magnetic field is going to be perpendicular with respect to the electric field. So this is the magnetic field at location A, of course, is coming out of the page. So coming out of the page would be this one, and this one would be going, magnetic field is going inside the board. All right, and there right here electric field and magnetic field is 0. Magnetic field is 0 because electric field is 0. So this is the EM waves created by electric field and magnetic field. So this is the EM waves, and EM waves are actually the light. EM waves are actually the light. All right, EM waves are actually the light. Now what is light? Light is C, and what is C? Lambda frequency over n. All right, so when EM waves moves and propagates in a space, in a vacuum, perpendicular with respect to each other, because electric field is perpendicular with respect to the magnetic field, we human perceive as a light. Let's consider the red light. Let's consider the red light, because this is in the vacuum. This is C is 3 times 10 raised to 8 meter per second. Let's prove that. So what is the lambda? Is always going to be C, 3 times 10 raised to 8 meter per second, no matter whether it is red or blue. So let's see, let's prove it for the red light. So C for the red light is, lambda for the red light is 700 times 10 raised to -9 meter, and the frequency is 4.3 times 10 raised to 14 hertz. 700 times 10 raised to -9, and 4.3 times 10 raised to 14, and of course 1. So red light is 3 times 10 raised to 8 meter per second in the vacuum. In the later, I'm going to help you understand red light, the speed of light changes when you changes the medium. So this is EM waves. EM waves created by what? Electric field, oscillation of electric field and magnetic field. Why they oscillate? Because electric field create the magnetic field, magnetic field create the electric field create the magnetic field by Coulomb's law and Oersted law together, and magnetic field create electric field by, of course, Faraday's law. What is Faraday's law? EMF is equal to, of course, negative N flux over delta T. So electric field creates magnetic field create electric field, which oscillate, which needs no medium to move. We human perceive that as light. We call it C, and it has a value 3 times 10 raised to 8 meter per second. If lambda, for example, go up, then frequency must go down, keeping the speed of light. What is our question? Does sound wave does sound wave move faster in the water than in the air? Well, to answer this question, or to even make a hypothesis, we have to look at the behavior of light. Now, if you look at the light and you see light changes the medium from air to water, light slow down. In the air, light moves 3 times 10 raised to 8 meters per second. In the water, light moves much slower than that, 2.5 times 10 raised to 8, because index of refraction in the air is 1, index of refraction in the water is 1.33. As a result, light, when it changes the direction, slow down, whatever the sound. So now, we should make a hypothesis: sound also slow down when it changes medium from the air to water. In fact, the sound moves faster in the water than the air. What did you just say? Sound moves faster in the water than in the air? Does that mean sound also moves faster in the solid than the water? This should be an aha moment for you, just like it is an aha moment for me. So let's enjoy your aha moment and then start the investigation, and let's start the investigation right now. Let's check 3 state of matter, gas, and then solid. The gas, the particles are very spread around. The liquid, they are not that much spread around. In the solid, they are very tightly held. What does that mean? What that has to do with the sound wave, the speed of sound wave? Well, velocity is very small, velocity is bigger, and velocity is very big, velocity of the sound wave. Why is that? That's because this is less steep, this is stiff, and this is stiffer. What does that mean? Small k, big K, and even big K. As the K bigger, speed of sound also go big. Now we're gonna see that this is our hypothesis. Now the next question is, what speed of sound depends on? It depends on 2 things. Our investigation shows speed of sound. Sound really depends on 2 things. One is the density. We're gonna use rho as the symbol. Other one is compression. How easy or hard to compress something, and we're going to use B, and sometimes compression also called bulk module. Alright, now let's check the density on this side and the bulk module or compression on this side. The density, we know rho is equal to mass over volume. So if the mass go up, what do you see? If the mass go up, the inertia also go up. So then velocity has to go down. Okay, so what is the relation? The relation of velocity and the density is inverse of each other. Now let's see what is the relation over here. The velocity and the bulk module or compression, or sometimes called pressure, is proportional to each other. Now then, what is pressure or bulk module? The bulk module is the force divided by area. So now let's see then what should be the formula. The speed of sound. The speed of sound formula should be then B over rho. Now we have to investigate by dimensional analysis whether we should add or whether we should modify this equation. So this is our basic equation. Now we're going to modify based on our dimensional analysis. So let's do the dimensional analysis. So what is then the rho? Rho is SI unit for mass is kilogram, and SI unit for volume is cubic meter. SI unit for force is Newton, SI unit for area is of course square meter. SI unit, if you break down the Newton, you see kilogram, meter per second square, and then there is a meter square over here. So this is for bulk module, and this is for rho. One on the top, B gonna go top, this one kg meter second square and meter square, and then we're gonna put this one kilogram over cubic meter, complete the dimensional analysis. Kg meter second square over meter square times, you flip them, cubic meter over kilogram. So you see kilogram cancel, meter square, so meter, so is meter times meter is meter square, and second square. Then you take the square root, you get meter over second. That's the SI unit for velocity. So then you have to modify this equation. So velocity of speed of sound is indeed the square root of bulk module and rho.